Okay, so I want to talk about alloys as defects, and this is of course from chapter 4 in your material science textbook. So just some definitions. An alloy is a blend of different metals, and you start off with, say, a pure material, and then you add impurity atoms to it. And you do this intentionally so that you can get certain characteristics of the material that you like. So for example, instead of iron, you might want steel, so it's more resistant to rusting. Instead of copper, you might want brass, so that it's a little tougher and harder. Instead of aluminum to make your airplane out of, you might want duralumin. You might not have heard of this one. This is a particularly cool alloy that they make airplanes out of. They make airplanes out of it, of course, because aluminum is a very light metal. It has a low density, but it's also really super soft in its pure form. So if you add dopants or impurity atoms of things like magnesium, manganese, and copper, then you make a harder, tougher alloy that's still very lightweight and maximizing all the properties that you want of that blend. So basically, when you do this, you're creating a solid solution, a mix of different things dissolved in other things, okay? You add these impurity atoms to the host maintains its crystal structure up to a threshold point, and it's compositionally homogeneous. Now you can look at two different outcomes if you add an impurity, which we'll call B, to the host, which we'll call A. So first of all, if you have your solid solution of B and A, then what can happen is that the B atoms, which are pictured here in gold, can just replace one of the A atoms in its lattice position. And this happens if they're similar in size and have some other criteria that are satisfied. And it's called a substitutional solid solution. One example of two metals that form a substitutional solid solution are copper when you add it as a dopant to nickel. Or you can have what's called an interstitial solid solution, and that's what happens if you have a large difference in the radii between the two different materials. And this is, for example, carbon that you add to iron to make steels. This is an interstitial solid solution because the carbon atoms are so tiny that they can just fill in those little potential wells that exist within the iron lattice. Now we'll study phase transitions and what happens as you increase the percentage of different dopants within the matrix later on. We'll study that in more depth. But what happens is as you increase the percentage, what will happen is they form these little nodules or these little separate phase particles, because things can undergo phase transitions as you increase the composition of the dopant material. So that's something for later. Okay, but if we're still back where we are today with our little substitutional solid solution that makes a nice homogeneous mixture, then the conditions for a substitutional solid solution are given by the Hume-Rothery Rules, okay? And there's 4 different things that you need to think about. The first is that the atomic radii of the two metals can't be that different. They should differ on a percent difference basis by no more than 15%, for example. They should also have similar electronegativities. In other words, they should be close to one another in the periodic table. They should also have the same crystal structure. It's really hard to mix, for example, a BCC crystal in with an FCC lattice. That's kind of hard to do. And then all else being equal, a metal will have a greater tendency to dissolve a metal of a higher valency than one of lower valency. And remember here, the valency is the number of electrons in that outermost energy shell. So let's look at some possibilities, some applications and questions applying these Hume-Rothery rules for solid solutions. So there's 2 questions that we're going to examine. The first is, would you predict more aluminum or more silver to dissolve and form a substitutional solid solution in zinc? And the second is, would you expect more zinc or aluminum to dissolve in copper? And so what we're going to use to answer these questions is this little table right here. This is from your textbook. It gives you the element, the atomic radius of the element, the kind of crystal structure that it likes to form on its own, the electronegativity, and the valency. And we're going to use those 4 things applying the Hume-Rothery rules. So first of all, let's answer question number 1. Would you predict more aluminum or silver to dissolve in the zinc? So if you look at the radii of aluminum and silver, then you see they're given here 0.1445 and 0.1431 nanometers, and then the radius of zinc is 0.1332. So the radius of zinc is lower than both of these two. If you calculate the percent difference that the silver and the aluminum make with the zinc respectively, you get 8.4% difference and a 7.4% difference. Now both of those are less than the threshold value that was given of 15%, and they're actually not all that different. So this probably isn't going to be the deciding factor, the radius here, because the radius of silver and aluminum is pretty similar. The next thing to look at might be the electronegativity. Well, aluminum's electronegativity is 1.5, and that's close to zinc's value of 1.6. But if you look at the value for silver, its electronegativity is 1.9. So in other words, the value of aluminum for its electronegativity is a lot closer than zinc's, and that would suggest aluminum might be the answer. But let's look at the rest too. Okay, so if you look at the lattice structure, aluminum and silver are both FCC lattices, face-centered cubic lattices, and zinc is hexagonal close packed. So since aluminum and silver have the same structure and neither of them match zinc, then that's not really going to be the deciding factor. And then finally the valency. If all else is equal, you look at the valency, it turns out that the valency for aluminum is higher than the valency for silver. The valency for aluminum is +3 and silver is +1. So you would expect silver more than you would expect, you would expect aluminum more than silver because of the electronegativity and the valency. That's the deciding factors. Okay, let's look at question 2. So question 2 said, would you expect more zinc or aluminum in copper? Okay, well, if you look at the radii, there's a 12% difference for aluminum from copper. So the radius for copper here is 0.1278, aluminum 0.1431, and then zinc 0.1332. So you can see that the copper is a lot closer to the zinc than the other. And so the aluminum has that large 12% difference. Now they're both still less than the threshold, but 12% versus 4% is a pretty big difference. Now copper and aluminum are both FCC, but zinc is HCP, right? So that means the zinc doesn't match. So that would have you leaning a little bit more towards the aluminum versus the zinc. Aluminum also has a higher valency. But aluminum and zinc have similar electronegativities. So given that you have more matches for the aluminum than the zinc, you're probably going to go with the aluminum. Okay? All right. Now, for the interstitial solid solutions, basically what's happening there is that they're falling into those little vacancies that exist within the lattice of the material, the host material. So for example, for here we're going to look for problem 4.5. Lots of times the geometry of the situation will dictate what the upper limit on the radius of your dopant can be, okay, because it has to fit within those little vacancies. So problem 4.5 says, for an FCC crystal structure, there exists an octahedral interstitial site, which is located at the edge, the center of each edge of the unit cell. So compute the radius of the impurity atom that will just fit into one of these sites in terms of the atomic radius of the host atom. So here's the solution to that. If you look at a face-centered cubic, remember that what happens in a face-centered cubic is that you have on each face of your cube, you have these 5 host atoms here that I've depicted in green. So there's one in the center and then one on each corner in an FCC structure. Now the interstitial site that they're talking about is here along the top edge. I've colored that interstitial site here in this kind of deep red color. Okay? So what's happening is it's just fitting there in the widest point of that vacancy, or in the narrowest point between the two spheres there. Okay, now if you assume that this is an FCC cubic lattice, then each of the centers of these 4 corners forms a square, and we're going to call the dimensions of that A. Okay, so the length of the side of the square is A, and since it is a square, the diagonal of the square will be √2 times A. Okay, now we're going to call the radius of the host atom, the larger atom, big R, and we're going to call the radius of the little substitutional material little r, because it's going to be a small radius. So just using geometry, if you look at the length of this side here, then A is the total length, and you can see if you connect center to center for these host atoms, connect center to center, that that length A is going to equal to 2 times the radius of your host atom plus 2 times the radius of your interstitial atom. And then what we want is an expression for the interstitial atomic radius in terms of the host radius. So I rewrote that expression: 2 little r equals A minus 2 big R. Okay? Now, we can also write what our value of A is in terms of the radius big R, and then we can sub in for A. So if you look across the diagonal here, the diagonal gives you 2 full diameters of the atoms, which is 4 times the radius, and 4 times the radius is going to equal that root 2a. And then I can sub in, a would be 4r over root 2, I can sub in 4a into my top equation and get this expression here. When it's simplified, I get 2 little r equals big R times 4 over root 2 minus 2. And then I can solve for that little math expression, 4 over root 2 minus 2, and I get 0.828. So 2 little r equals 0.828 big R, or when I solve for little r, I get 0.414 big R. So that's the ratio, basically, or the factor there that relates your little radius for your interstitial atom to your big radius. And it was just solely determined by geometry. Okay, now, in terms of how we talk about alloys, the way that we usually do it is we give the percent composition. We can do that in one of 2 ways. We can give the weight percent composition, which is really super common because the engineers just weigh out how much of each component that they want in their alloy, or you can give the atomic percent of each component. Excuse me. So if you have a 2-component system, then the weight percent for component 1, which is called here C1, is going to be the mass of component 1 divided by the total mass, which for a 2-component system is just M1 plus M2. And then put it in terms of percent, that will give you a fractional composition, and then you multiply that fraction times 100%. And that gives you your weight percent. Now, of course, if you have an alloy that's an alloy of multiple components, then all you would do is, instead of M1 plus M2 on the bottom, is you would put the sum of all the different components, M1 plus M2 plus M3 plus M4, whatever, and you would just leave M1 there on the top. Okay, so that's how you would do your weight percent. In terms of an atomic or a mole percent, what you would do is, to get the percent composition, you would multiply 100% times the number of moles of component 1 divided by the total number of moles for the system. You could also do atoms if you prefer that. Now, your book takes these 2 very simple formulas and it derives a whole host of formulas in this section that all come from these 2 formulas. I am not going to go through each one of the, I think, 10 to 15 formulas that it goes through in that section. Please read it, and you can see it goes through, how to find the average density, how to find all this stuff, and we don't need to worry about that. You just read that section and you'll be just fine. There's some more conventions that are kind of fun for talking about percentages of alloys. You've probably heard of the carat system that's used in gold alloys, for example. So basically, the, the purity in terms of its percentage is just going to be the gold carat value divided by the total. So they consider 24 karat gold to be pure gold. 24 karat gold is pure gold. So that would be your total on the bottom of the fraction, and then whatever else you put on the top. So if, for example, you have 18 karat gold, then you have 18 divided by 24, and that gives you 75% gold. So in other words, if you have 18 karat gold, you have 18 parts gold and 6 parts of whatever else you're mixing in, for a total of 24, and then 18 divided by 24 gives you 75%. So that's how to do the conversion from the carat system over into, for example, the weight or mass percent, which we're more familiar with. And this is 12 karat gold, for example, would be 12 parts gold, 12 parts another, and that's 50% gold, so on and so forth. Now, I stole these prices off the internet. Of course, prices fluctuate from day to day, so if you look up the price for gold now, it might be different from what's displayed on this slide because there is a lot of fluctuation. But gold is a very expensive metal. It's a precious metal. And the other metals also fluctuate from day to day based on demand and supply. On the day that I originally made this slide, gold was $1,380 per troy ounce. The economy was in a really bad state, so gold was $1,380 per troy ounce. Platinum was actually more expensive than gold at the time, and it was $1,480 per troy ounce. It fluctuates. Right now, I think today, platinum was a little less than gold, but you know, whatever. Palladium, another one, $700 per troy ounce, still quite an expensive metal. But nickel and copper are cheap. So nickel and copper are $7 and $2 per pound, not per ounce, per pound, so it's really cheap. And silver today was $15 an ounce. So understand that all these different metals have their own monetary value. So that would mean that not all gold is truly of equal monetary value, even if it's the same carat weighting, because it depends upon what other metals are in the mix in the alloy. Weirdly enough, though, sometimes they don't price things that way, so that's interesting. So, for example, there's different types of gold. If you go to buy jewelry, you might hear the jewelers speak about yellow gold, red gold, rose gold, pink gold, or white gold. And those are different colors that the gold can take on, and those depend upon what the gold is alloyed with. So, for example, yellow gold is mostly gold with a little bit of silver and copper and zinc. Okay? Red gold has copper mixed in with it. Rose gold has copper and silver mixed in with it, and so does pink gold, just in different concentrations. And then white gold, which is really hot right now for engagement rings and wedding rings, has, depending upon what the alloy is, platinum, palladium, silver, nickel, or zinc mixed in with it. Okay? Now, of course, platinum can be more expensive than gold at times. Palladium is still pretty expensive, but it was about half the price of gold. Nickel, cheap. Zinc, cheap. So depending upon what the gold is alloyed with, the white gold, it might dictate a little bit your price. I don't know. I haven't really done a lot of pricing of white gold. If it doesn't, it should. Now, I stole this off a jewelry website. This is pretty interesting. There's some issues with white gold, okay? This is something to bear in mind if you're going to be looking or in the market for an engagement or a wedding ring. People are all excited about these white gold engagement rings these days, but one thing that they do is they fade in color. They're not as shiny and bright at year 2 as they were in year 1. The reason is that these white gold rings that they typically sell, they usually plate. Okay, they put a thin layer. Plating is putting a thin layer of another metal on top of the base metal. What they usually plate it with is rhodium. Okay, so rhodium is also quite expensive, but because it is a plate, it has a tendency to flake off after a year of heavy wear. So you might need to get your white gold ring replated every once in a while, which is probably not going to be all that cheap because rhodium is not cheap. Also, remember that you might have to think about any allergies that you might have or the person might have that you're buying the ring for when you get the ring. If they have an allergic reaction to certain metals, then that could cause irritation. And people in general, on average, have more allergic reactions to white gold than they do to yellow gold. So that's another thing. Next, in terms of repairs and resizing, yellow gold is really easy for the techs to work with because yellow gold is usually got mostly gold or some copper and silver. And copper and silver and gold are all more malleable and ductile than the things that they usually put in the white gold, like the palladium and the platinum and the nickel. Those are more brittle metals, they're less malleable and less ductile. And so if you want a truly seamless repair for any jewelry that you might have, you would probably go for the yellow gold over the white gold. Now, what they say on the jewelry website is something that I actually sort of disagree with. But it seems to be the industry standard. They say yellow gold, white gold, and even rose gold have the same value providing the assay or carat is the same. They base that on the argument that 14 karat gold is 14 karat gold. In other words, it has the same weight percent gold regardless of what you're doing because it is 14 karat, right? So if you've got an 18 karat ring, it's 75% gold. And then they say, well, since it's got the same weight percentage of gold, it should be the same price. But wait. if you have a white gold ring that's been alloyed with platinum, platinum is very expensive, then that should be more expensive than a white gold ring that's been alloyed with palladium, which is half the price of gold. And if you have a white gold ring that's been alloyed with nickel, although that's not common anymore because so many people have allergies to nickel, but if they do, that stuff is dirt cheap. And so that white gold ring should technically be cheaper than the white gold ring that's been alloyed with platinum or palladium. So, in my opinion, they need to do a little bit more thinking about that. But who knows? Now, if you take your ring to a pawnbroker or you're trying to, just value the price of your jewelry or whatever, they're going to test your ring to see what the carat rating of the ring is. The way that they do this in general is that gold is very resistant to reactions with all but the strongest acids. It's very resistant to reaction. So what they do is they take your jewelry, they take a special stone, they rub the jewelry on the stone so they get a small trace amount of the metal on the stone. And then they put different acids on the stone on top of your metal rubbing and see if the acid can dissolve the metal or not. Okay? If it dissolves it all very easily at a low, with a weaker acid, then it's not gold at all. If then they have a scale to test. If you dissolve it all and there's this really green reaction, then it's not gold. Okay, it's some other base metal and it's not gold. If you have with the different strengths of acid, what they do is they vary the strength of the acid going left to right with the rubbing, and then when the metal rubbing completely goes away, depending upon the strength of the acid, that'll tell them what the carat rating of the metal is. So that's pictured here in this little graphic. So they took a rubbing of the different metals, they did the acid on it in the rubbing, they rubbed the acid across the top, and then that told them what the rating of the gold was. So that's kind of fun. Another way that you could do it would be totally non-destructive is if you could measure the density of the metal. So what you could do, of course, is do a water displacement method to get the volume and then measure the mass, divide the two, and you have a density. To show you what this would mean is, let's figure out what the average alloy density for 18 karat white gold would be if it were alloyed totally with either platinum or palladium. So to do that, I'm going to use one of those many formulas derived in your book that started with the weight percent. Okay, we're going to figure out what our average density is. So the formula for the average density for a two-component mixture, the average density is equal to 100% divided by the percent composition, the percent by weight of material 1 divided by material 1's density, plus the percent of material 2 divided by material 2's density. So in that formula for my average density, I'm going to plug in my values for the gold and for the platinum and the palladium. So first of all, 18 karat gold, 18 divided by 24 gives you 0.75, and that means that you have 75% by weight gold. Now the densities of gold, platinum, and palladium are 19.32, 21.45, and 12.02 grams per cubic centimeter respectively. So for the average value of the density for the platinum, we have 100% over now the denominator, 75% divided by 19.32 plus 25% divided by 21.45, which gives you an average density of 19.81 grams per cubic centimeter. So that's the average density for your platinum alloy. Now for the palladium, you have 100% divided by 75% over 19.32 plus 25% divided by 12.02. Now because the density of palladium is a lot lower than that of your platinum and your gold, it brings the average density down to 16.77. So that is something that you could probably easily measure in a lab, so you could determine your average density to see what the value of the weight percent is and what it's alloyed with. Okay, so I hope that was fun. There's some information in this lecture that isn't contained in the book. I hope you enjoyed it.